Japan. I was in Tokyo. Okay, but now about the research lines that I want to present here today. So basically my research is placed at the interface between computational chemistry and molecular astrophysics, or I would rather say in my case astrochemistry, because I really study the chemical processes that occur in the interstellar medium. And the research line broadly defined that I carry out in my research are astrochemistry using machine learning, and in this case I will now refer to the first part of my research, that is using interatomic machine learned potentials to study physical processes on ices. Second, surface chemistry on interstellar ices. So I studied the reactivity that occur on interstellar ices at very low temperatures, both from a computational chemistry perspective and also an astrochemical modeling perspective. And these are two more applied, maybe, research lines that I have undertook in the last year. So one of them is the study of isomerism in interstellar medium, so how different isomers came to be in regions with very cold and very extreme conditions. And finally, last but not least, the research line that I carry out in collaboration with Maria, that deals with how pHs, so molecules that are composed mainly of carbon and that are structured that are much higher than we would expect, or much larger than we would expect in the interstellar medium, came to be. The overarching goal of my research, I would say, is to link the very, very elemental atomistic processes that occur at very low temperatures and not so very low from time to time with prebiotic chemistry. So how molecules, ever-growing complexity can appear in the interstellar medium. Great. So, well, this is also a little bit redundant, but I think it's important nonetheless for the PAMS department in the institute. So, as I said, I work at the crossroad between chemical kinetics, molecular physics, and astrochemistry. And for that, I use a plethora of different techniques that intersect in the different connections of the different disciplines. So, for the sake of keeping this brief, I use electronic structure theories that I couple with molecular dynamics simulations. And I train different types of potentials. It depends on whether I use on-the-fly simulations or I use embedded techniques or neural network potentials. And I unveil reaction mechanisms for different molecules that occur in space. And the chemical kinetics that I carry out, I do it with microcanonical transition state theory, or RKM. I use also capture theory, instant bond theory, and so on and so forth. Let's go into the scientific context, so the contextualization of my work. So as Pablo presented before, we are very accustomed to the cosmic matter cycle, and we have different regions in space, and every region is characterized by a distinct chemistry that provides, I would say unique, but not so unique, but well, for the sake of not being also very thorough, I would say very unique fingerprint of the chemistry of the different regions in space. That helps us, of course, to understand different astrophysical properties. My research is mostly, or for the time being, this is changing right now, but I've been working mostly in dense clouds. Dense clouds are regions of space that are very cold, relatively dense, and they have a series of conditions that are conducive to chemistry. So the main reason why these molecular clouds are considered the greatest laboratories in existence is that they have a dusty envelope over here that avoids photons to fully penetrate into the cloud, and this protects the molecule for breaking apart through photodissociation processes. And this is precisely why, in these kind of regions, we have detected more than 300 interstellar molecules to date. And within these very huge objects, we have two main phases where chemistry can happen. We have the gas phase, and also we have dust grains that encompass around 1% of the total mass of these objects, with temperatures around 10 Kelvin. The most important thing of this slide is that within these regions, we have two different regimes for the chemistry. We have chemistry in the gas that has their rules, and also chemistry on ice, well, on dust, that this is a spoiler, it is covered by ice. And this leads to a completely different chemistry, normally. And if we could understand all the reactions that happen in the gas and on the grain, and also taking a very simplistic approach, we could solve the chemistry in these regions just by solving this rate equation, in which we have just a balance between the molecules that are destroyed, the molecules that are formed, and in two different mechanisms overall, which are bimolecular and unimolecular. This is not really important, but the objective that we have is that we want to map all the different interstellar species, simple or not, with other more complex using, normal chemical kinetics. The main problem is that to date we have around 13,000 reactions with more than 100 and 300 species in the reaction networks. They are not detected, many of them, and some of them are include the reactions on the grain and on the gas, and they are distinct in the models. But overall, we have around 1,300 species. And this is really the biggest conundrum of astrochemistry. Most of the rate coefficients and the reactions that are considered in these models are totally guessed. So they are put into the reaction networks just by chemical intuition, or even not, even without that intuition. Don't get me wrong, so these kind of models have been very, very useful in the past. So that is really something that has advanced the field, but we can do better right now. And in order to construct a chemical model that can solve this kind of chemistry, we have a series of different processes. This is a snapshot from the chemical model that we use at the University of Tokyo, now here, of course, that includes all the different types of reactions that take place that we assume takes place in the interstellar medium. You can see there the usual suspects: two-body collisions, radiative association, two-body reactions on grains, adsorption, desorption, and so on. And as I mentioned, we have two clear rules. First of all, we have reactions in the gas, exemplified in the top square or rectangle, in which this is not totally general, but in general, we have reactions that are bimolecular in the gas. So we have two-body reactions that lead to two-body products, except in the case of radiative associations. However, in the case of the ice, and because the ice normally acts as a third body, dissipating the heat of the reaction, what we have is elementary steps that can build chemical complexity. And this is something that is traditionally considered in the field. So reactions on the grain lead to more complex organic molecules, such as, for example, the prototypical formation of the simplest, or one of the simplest organic molecules, methanol. Okay, so with that in mind, let's take a little bit of a detour into the historical context of what I'm saying. So I have said that the reactions on the gas usually take place in a bimolecular context, and this is what it was thought before more or less 2006, with some question marks. So before 2006, methanol, which as I said is the most important complex organic molecule, I would say, was thought to be formed via this sequence of reactions over here. Okay, so basically we would have a radiative association followed by a dissociative recombination by an electron. An electron comes to a molecule and breaks the molecule apart, giving us the neutral, that is the one that we wanted. What happened is that when experiments measured the ratio of the products of this reaction, showed that actually this reaction channel, that it was previously thought as the most important, was very, very minor. So this really collapsed our understanding of how methanol could form, and we needed to rely on, or at that time, they needed to rely on different theories to form methanol in space. Basically, basically through grain reactions of the hydrogenation of carbon monoxide, that is one of the simplest molecules. And then, I'm sorry for the quality, this was perfect in my computer, but well. So, well, so yeah, it's more or less, one can see it, yes. So, what? Oh, okay. Well, nonetheless. So we can decompose this kind of grain chemistry into 4 elementary processes, not considering energetic processes, into the combination of accretion, or the position of molecular material on the surface of ices, diffusion, of how the molecular material moves around the surface, desorption, of how the molecule leaves the surface, and reaction, which is when two particles collide and they overcome the activation barriers, if any, to form the new molecules. Great. So this is precisely what I have been studying in one of my postdocs, at least, try to give an atomistic description of every of these elementary processes that occur on ices. Great. So, but first of all, let's consider what I meant when I talk about ices. Well, ices or dust grains in space are, in particular in dark clouds or in dense clouds that I have presented before, are made out of a refractory material, so for example silicates or carbonaceous material, and because the temperatures are very, very low and the molecules that accrete on top of this material cannot return to the gas phase, when the temperatures are low enough, an ice mantle starts to form, whose main component is water, but it also has a seasonal, or well, I would say an epoch dependence, with different components being more important in different times of the evolution of the cloud, or even farther than the cloud. For example, carbon monoxide, carbon dioxide, and methanol. And it's in these ices where the reactions takes place, at least the ones that I study. And these ices have a particularity. So instead of what we expect on Earth, that we expect the typical ordered crystalline ice, what we do have in space, actually, in most cases again, because we cannot really draw an absolute conclusion of what happens in space, because we are in space overall, after all. So they are amorphous. So we need to simulate systems that are amorphous in nature, and this implies a series of approximations in my research that I will cover. The most important thing here, of course, is that the potentials that we need to study these kind of systems need to be anisotropic. So we cannot really simply use a typical crystalline solid and calculate things on it, because it wouldn't work here. And the typical ways of overcoming this limitation is to use periodic slab, but with some amorphicity, and study them with DFT. Similarly, if the process that we want to study, the DFT, by the way, density functional theory, which is an approximation of how to solve the Schrödinger equation. Clusters and DFT, if the problem that we want to solve is very local, we can use simply a cut of an ice and study them there, or classical force fields. Both of all of these approaches have advantages and disadvantages, as the technique that I use. Of course, it also has advantages and disadvantages, and what I use for studying these physical processes are neural network potentials. Using an in-house model that we develop at the University of Stuttgart and we use at the University of Stuttgart, we create interatomic potentials able to simulate these kind of amorphous systems for the treatment of ices with thousands of atoms. This is the best we can do. And the nice thing, so the neat thing about these kind of potentials is that they can simulate the formation and destruction of chemical bonds, something that will also be important in order to study reactivity, of course. But these kind of systems, or these kind of potentials, are very expensive to generate and require to have a prior knowledge of the system. So they are not generally applicable, at least at the stage that we are now. So we need really to decipher a little bit the physics of the system, or better said, the chemistry of the system before applying it. But we have, well, this is a quick reminder of the system, of the processes that we have simulated using machine learning potentials or neural network potentials. And we have success in applying these kind of potentials to treat the systems or the processes that I was talking about. So over the years, we have worked in simulating absorption of atoms and simple molecules on interstellar ices. We also have constructed the free energy surface of a full amorphous, or well, a cut of an amorphous surface in order to study diffusion, and we have been able to obtain diffusion constants out of it. And lastly, and here we have a recent paper also that was accepted, we have succeeded in using these kind of potentials to study reactivity and non-thermal processes that occur on the ice, such as, for example, here I show what happens when a molecule such as pH, so phosphorus and hydrogen, form and reacts and collides with the ice and have a series of energy transfer processes that lead to the desorption of the molecules. This is, by the way, the mechanisms one of the mechanisms for which we know that molecules that are formed on the gas, on the grain, can return to the gas. And with that, I have talked about the physical processes. I will be very glad to answer any questions that you have about the methodology. But since I want to cover all the different research that I have carried out in these years, I want now to talk about chemical reactivity in the gas, in the grains, and also in the gas, but I have not included so much about how I treat the gas phase. So the problematic here is that we have a pace of molecular detections in space that very, very much surpasses our attempts to understand it. So most of the molecules that have been detected recently in space, we don't know how they are formed. And this is the purpose of this line, to know how these molecules are formed. Detected or detected recently or in the past. So many of these molecules, even if they are being detected for 10 years or 15 years, do not have a clear synthetic pathway. And basically in this research line, what we do is to construct complex chemical networks that are able to explain the formation of the different molecules. So these are simply two examples of the that we have published over the years. Here, for example, we explain an alternative way of forming methylamine, or different molecules that have this skeleton, this kind of skeleton in which we have a parent molecule that is a very simple hydrocarbon. And in order to do this, we need to simulate two different processes that occur on the ice. We have two different mechanisms mainly that contribute to the formation of these molecules. We have the traditional Langmuir-Hazelwood mechanism, that is a mechanism that occurs on surfaces where two pre-absorbed molecules move on the surface, or at least one moves on the surface and encounters a reaction partner and reacts. And also the LA radial mechanism, in which this is a bimolecular mechanism in which a molecule or an atom from the gas collides with a pre-absorbed adsorbate on the ice. And these both types of chemistry are simulated in my research. And we have another different limitation, or a different categorization of the different projects that we carry, and is in systems that we expect that do not have huge activation barriers. These are systems in which we have barrierless reaction. Every diffusion event that makes two molecules close will lead to reaction. What we study basically is the surface influence in the reaction. As you can imagine, as these surfaces are amorphous and they have, in general, water and hydrogen bond networks that form upon the adsorption of a molecule there, this really causes an effect in how this molecule react with the different agents, such as, for example, hydrogen atoms, oxygen atoms, and so on. And in systems that do not have a barrier, we can really dedicate time to take a look at how the interaction between the molecule and the surface plays a role in the outcome of the different reactions or the different barrierless channels that influence the chemistry. And in systems where we do have activation barriers or activation energies involved in the reaction, we use very simple models. Sometimes we even just fix the rotational partition function of the molecule and study with different theories how quantum tunneling affects the chemical reactivity. And here I show an example on a hydrogen abstraction. That means this hydrogen of the phosphine goes to another hydrogen and releases H2. And this reaction is, of course, mediated by tunneling, and we have calculated that over the years and include in astrochemical models. This with respect to Langmuir-Hazelwood chemistry, but as I said, I also studied LA radial chemistry, and in particular the chemistry of carbon atoms. So you can imagine a carbon atom in the gas that collides with an ice and does something. But what carbon atoms do, that they tend to be very reactive, and instead of the usual way in which we thought reactivity occurs on ices, what we showed actually is that the ices in this kind of LA radial chemistry partake in the chemical reaction, and we have proton shuttles on interstellar ices, something that we proposed in 2022, that we extended also to ices with ammonia, mixtures of water and carbon monoxide, and so on. And that led us to develop a new carbon framework in the ISM that we published in 2023, in which we can explain the formation of ever more complex molecules on the surface of ices by carbon chemisorption on different binding sites in which we have chemicals ready to react, and also we need some contribution of physisorption states on the surface. So that is something that we have done over the years as well, in collaboration with my colleagues at the University of Hokkaido. And the last part that I want to talk about the methodologies that I use is astrochemical kinetic modeling. And returning to the very beginning, astrochemical kinetic modeling is basically solve this equation for a physical conditions that are compatible with interstellar dark clouds. And now what you can see is that my research merges quantum chemical calculations with the inclusion of that quantum chemically derived magnitudes into these kind of models. I won't show many projects regarding this, just one that is probably the last one and also the most visual one, in which what we took a look at is what happens when in a chemical model we take into account the heterogeneity of the different interstellar ices. I have been saying during my presentation that interstellar ices are covered mostly by water, which is something that is true, but in some stages, carbon monoxide, that is forming the gas, lands on the ice and readily creates an apolar surface in which chemistry is different because the dipole moment of CO and water is radically different. And this in turn has an effect on the models that was not taken into account until we publish it. That is that this is the rate constant or the rate constant for Langmuir-Hiselwood mechanism depends on the times of diffusion of molecules on the surface. But this time of diffusion, in turn, depends on how the molecules bind to the surface. And this is a simple representation of what we did, but it's quite loyal to reality. Because what we did is combining, again, quantum chemical calculations with astrochemical modeling. What we did is to compute the ratio between the binding of molecules on CO clusters and water clusters, finding that, as chemists probably would know without calculations, the binding energies vary in the different surface by a factor, and this is what is not trivial, by a factor more or less of 0.4. And the next step that we took is just to implement, and in the first approximation, a linear term that takes into account the coverage, the surface coverage of water and carbon monoxide, and modulates the binding energies or the affinities of the molecules with the surface accordingly. And run chemical models, many chemical models. I will just summarize them. And I will show what is the effect of varying these binding energies and including this kind of heterogeneity of the surface for a couple of, well, 4 molecules, which is acetaldehyde, dimethyl ether, ethanol, and methyl, this is acetic acid. On the right-hand side of every panel, what I show is the previous model. So the model without incorporating carbon monoxide, chemistry on carbon monoxide. And on the left-hand side panel of every one of them, what I show is what happens when we include carbon monoxide into the model. We see that there is a window of different physical conditions. Here are shown dust temperature or ice temperature and cosmic ray ionization rate, in which there is an increase, I would say a dramatic increase in the formation of complex organic molecules, which allow us in turn to propose newer scenarios for the formation of these molecules in space. Great. So now I reach the part in which I will present some new results that I have been carrying out at IFF. Basically, as I said at the very beginning, I'm very interested in the isomerism of molecules in the interstellar medium. And the molecule that is more important, I would say, one of the most important isomers, apart from HCN, that is, of course, the most important one, is formic acid. And in this work, that is close to be submitted, I would say, what we have done is to couple all the well-known chemistry of formic acid, introduce the isomeric dimension into it, and run chemical models such as the one that I just showed. And very funnily, in comparison with the Quixote data of TMC1 that some of you may have heard of, is an astronomical survey of the Taurus molecular cloud, which is one of the richest sources in the sky for chemistry. We observe that more or less the time scale of the cloud, we observe, or using this updated chemistry, almost perfect match between the ratios of observed trans formic acid and cis formic acid. Mainly due to a mechanism that we have labeled isomerization upon desorption, in which after forming formic acid, the molecule can undergo an isomerization non-thermally after the desorption. Great. Another work that I want to highlight here is, and this is for my colleagues at the molecular astrophysics department, is we have computed the binding energies, not of molecules on carbon monoxide, but of isolated carbon monoxide on water using different models for water. What we have done is using these interatomic machine learning potentials that I've been talking about, we have created different models of ice. We have created compact ice and porous ice, and we have obtained not a single binding energy, which is something that is commonly done, but a distribution of binding energies as a function of the binding site that we obtain, that we sample. This gives rise to a Gaussian function to fit the data. And what we have done in comparison with other models is, instead of using a single binding energy that usually is the average of the binding energies, we have introduced the full distribution of binding energies into a protoplanetary disk model, finding then a new concept here, snow lines that are so regions in space where the molecules that we consider are in the gas, or are in the gas, not in the grains, where molecules dissolve. We have found that carbon monoxide is actually very spreaded on protoplanetary disks in comparison to what was thought before. And finally, some recent news on another research line that we have started. This is, as I said, carried out by Maria here. So what she's doing, I haven't talked a lot about how I tackle gas phase chemistry, but this concerns gas phase chemistry. And now, as you may know, we are detecting a lot of polycyclic aromatic hydrocarbon molecules in space. They are very, very complex, so they cannot be dealt with simple quantum chemical calculations, because the search for the possible chemical reaction paths is prone to errors. So what I suggested Maria is to use automated techniques to sample very, very complex potential energy surfaces, stationary points on those surfaces. And so far, I'm very happy. She has succeeded. So she has found the low energy, so the low temperature formation pathways of C5H7+, I think, yeah, C5H7+, using automatic reaction discovery techniques in which we characterize up to 80 stationary points in the potential energy surface and obtain the corresponding rate constants. And the same for the reaction of propene with the cyano radical. So yes, I will keep you posted on the outcomes of Maria, of course. And well, this is my summary of the talk. So I want to indicate here my philosophy for my research. So I start every project by carrying out quantum chemical calculation of some quantity that is important for the chemistry of a given astronomical region. Then with my results, I translate those derived quantities into the realm of astrochemical models. And I run the chemical models to verify if my calculations make sense in an astronomical context and adapt accordingly if needed. So yeah, thank you very much.
So thank you, Herman, for this very nice talk. So questions? Yeah.
Okay, I have several questions. The first one is, in what extent what you are using in rate constants, the result